Final example, example 4, a boy of mass mb equals 40 kilograms is standing on the right edge of a raft that is 2 meters long with mass mr, so mass raft equals 20 kilograms. A camp counselor comes to hand him a piece of mail from the edge of the dock, but he can only reach out 1 meter. The boy can reach out 0.5 meters, but the left edge of the boat is 0.5 meters from the dock. Will the boy be able to walk over and get his mail without rowing the raft? Now the first thing you think is, yeah, of course he can walk over. He just walks over here and he grabs his mail, right? Wrong, it can't just happen like that. He can't just walk over, because if he walks over, what happens as he walks over? There's no friction between the water and the boat effectively, right? It's going to wind up getting moved. So there's no external forces on here. We don't expect water to resist. It doesn't give us much friction. So the boat is going to wind up sliding this way. The center of mass of the system will be preserved. Since the center of the mass of the system is preserved, by the time the boy gets to the left edge of the boat, he might only be over here. And it might be the case that the boat edge is now like this, right? As the boat and the boy represent a system. And we know the center of mass of that system will be preserved because there's nothing to keep it in place. There's nothing to hold in place. There's no external forces acting on the system. So as the boy moves around, the boat will have to move in response to that. Center of mass of the system has to be preserved. If you were an astronaut in space and you threw a wrench, the wrench would fly away from you, but in result, you would wind up floating backwards. Because one, we can think of it as the forces canceling one another out, but we can also think of it as the response force. You throw the wrench, and in response, throwing the wrench puts a force on you of the wrench on you. But we can also think of it as the center of mass of the system is preserved. They are the same thing equivalently. They're the same thing. The idea that forces come in pairs that cancel one another out is the same idea as the fact that the center of mass of a system isn't affected by its internal forces. They're equivalent. Great. So now we're going to have to get down and dirty and start doing some math. All right. So what's the center of mass of the system to begin with? Well, to begin with, we know that the center of mass of this raft, it's reasonable to assume that the raft is homogeneous, right? Or at least that it's symmetrical. So we can assume that the raft center is in the middle of it. The boy is at the edge at 2 meters. So we know that XR is going to be at 1.5 meters. And we haven't discussed yet what our coordinate system is. Let's make to the right positive. But where are we going to make 0? Well, in this case, we're going to have shifting motion between our before and after pictures, right? Before the boy starts to move and after he walks over. So it's up to us to figure out what is a good stationary reference frame that we can use. In this case, I think the pier is a great place to make x equals 0. The pier is going to stay there, and that's what we care about. We care if the boy can get 1.5 meters away from the edge of the pier where the camp counselor is. Camp counselor can reach out 1 meter, the boy can reach out half a meter. So if the boy can get to x equals 1.5 or less, he's good. He can get his mail without having to row. Great. If he can't, he has to ship out the rows and actually move the boat or swim over or something. All right, so at this point, we can solve for what the center of mass of the system is, right? So XR is equal to 1.5 meters and XB is equal to 2.5 meters because the edge of the boat was 0.5 and then the boat itself was 2 meters long. So what's X center of mass of the system going to be? M1 x1 plus M2 x2 all over M1 plus M2. So in this case, we've got M1 x1, we've got 1.5, the location of the raft, times the mass of the raft, 20 kilograms, plus, I probably should swap this since we're talking about M1 x1. So it's really 20 times 1.5, but I'm sure you understood what I meant. Plus M2 x2, mass of the boy is 40. Times the location of the boy is 2.5. We divide that by the two things put together, 20 plus 40. And that will wind up giving us, on the whole, 130 over 60. So the center of mass of the boat-boy system at the beginning is 2.17 meters. So if we think about where that is, that winds up being somewhere over here. Now, without even doing the rest of the math here to figure out where the boy can get to, we can figure out he's not going to be able to make it. How can we figure out? We know symmetry is going to work on our end here. The boy, if he moves here, is going to be directly over the center of mass of the system, right? So that means when the boy gets to here, the boat is going to wound up getting here as well. The center of masses for each of the objects is going to have to line up for the center of mass of the system. So that each of the objects is moved to the center of mass of the system, then the center of mass of the system is going to be where the objects are. Sorry. If the object moves to the center of mass, then the other object to compensate will also have to move to the center of mass since it's a two-object system. So that means if the boy is at one extreme here, then he's only going to be able to make that much farther a jump out afterwards. So the boat will wind up making out, its center of mass will wind up also getting out over here. So the boy, to get to the other maximum, is only going to be here. So the difference between that was less than half a meter to get to here, and then it'll be less than half a meter to get here, so he's going to be greater than 1.5 meters. We don't know the precise numbers right now, but we can at least tell he's not going to make it. But let's figure out what it is exactly for practice. So now we have to think about this again. So now we've got our after picture, right? Camp counselor standing here, still at x equals 0, right? But now the boat is there, and the boy is on the left edge, right? Do we know where the boy is located? We don't. That's the whole point of this. So xb equals question mark. Do we know where the raft is located? If we knew where the raft is located, we know where the boy is located. But exactly because of that, we know that the two are related. So we can think that xr equals xb plus 1, right? Because he's going to be 1 meter from the end because he's going to walk as far as he possibly can, right? So we've got that xr equals xb plus 1, xb is unknown, but we know that x center of mass is going to remain 2.17 meters from what we solved before. So if we know that x center of mass is equal to m1 x1 plus m2 x2 all over m1 plus m2, well, we know what our center of mass is. It's 2.17 meters. Mass 1, still the same mass, it's 20, but where's it on? It's on plus m2, the boy's mass is 40 times the location of the boy. Don't know where it is yet, but we will soon. The sum of the masses is 60. So we multiply 2.17 by 60, we get that 130 we started up with over there. We get 20xb plus 20 plus 40xb. We get 110, because we subtract 20 from each side, equals 60xb. And then we divide each side by 60, and we wind up getting 1.83 equals the boy's location at the end. So no, can't get male, right? He can't get male without rowing. Great. 1.83 is where he finishes getting up to, and we know this because we know that the center of mass of the system is going to have to be the same before and after because there's no external forces on the system. We know that there's a connection between where the boy's location is and where the center of mass of the raft is, and we can treat that as a point mass for the raft. So that gives us enough information to be able to solve for where the boy must land. And there you go. We just do some math and we're able to figure it out. All right, hope you understood this, hope it made a lot of sense, and I hope you enjoyed it. It'll be really useful when we're talking about momentum because that's the springboard that'll get us into being able to talk about collisions, which will give us like pretty much all we need to have a really deep understanding of kinematics and force. All right, thanks, have fun.